Indeterminate forms and L'Hopital's rule.
Make sure you put like.
I'm recording. Right. It's okay. I just didn't want you to say anything. I just didn't want you to say anything bad. All right, recall the forms. When we got 0 over 0 and infinity over infinity, they were called indeterminate. It's typical. And it's Friday. All right, so remember when we were trying to find the limits a long time ago, we had different ways that we found limits. One of those was by direct substitution, one of those by graphing, and one was by a chart that looked like this. We've done this. It's not a secret. But then sometimes we've got indeterminate forms where if we directly substituted, we got 0 on the top and 0 on the bottom, which would be an indeterminate form. And then we had to like simplify it. So we're going to go back, like your homework helps you do that as well to memorize that, or to refresh it. But we're going to do it in our notes as well. So it's not, like I said, it's not as complicated like the actual calculus part. The hard part is the reduction and the stuff, remembering how to like make it fit into that. So if you get those indeterminate forms where you have 0 over 0 or infinity over infinity, then you have to do more stuff. So they do not guarantee a limit exists. Nor do they indicate what the limit is if one does exist. When you encountered one of these indeterminate forms earlier in the text, you attempted to rewrite the expression by using various algebraic techniques. So we're going to talk about those really quick. So if we got 0 over 0, I'll turn it, sorry. For example, if we had the limit as x approaches -1 of 2x squared minus 2 over x plus 1. When we do direct substitution, what do we get on the top? Do you know what we're substituting? -1. So what's -1 squared? +1 times 2 is? -2 is 0. On the bottom, if we substitute -1, what do we get? 0. So there's your indeterminate 0 over 0. So we couldn't do that. If it were a number like 4, we would just plug it in and we would get the limit is whatever that is when you plug in 4. Okay, but when we get the indeterminate form 0 over 0, we had to do something. So what we had to do on this was we factored the top. When we factor the top, what do we get? Is this? Take out a 2, you get x squared minus 1, which factors into x plus 1, x minus 1. So all I'm doing is factoring. And the reason that I did that was then I could cancel out those x plus 1s. And now when you plug in your -1, so on the top, what's -1 minus 1? Times 2 is, so your limit would be -4. We don't have anything on the bottom to plug into. Everybody understand? So what did we do? We divided the numerator and denominator by x plus 1. So infinity over infinity. If we had the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. You get a graph. Sorry, it's really hard to see. You get a graph that looks like this, and it actually gives you infinity over infinity. So like if we're looking at just the top, where does the graph go as we approach infinity? So remember, infinity is to the right, all the way over. What happens to the graph? Goes up to where? Infinity. Does everybody understand why there's an infinity on the top? Same thing will happen on the bottom. Your 2x squared plus 1 is going to be up a little bit, and it's also going to be that U shape and go to infinity. So what we had to do is we had to divide by the highest power on the bottom. So what's your highest power on the bottom? So divide everything by x squared. So when we do that, we get 3 minus 1 over x squared, 2 plus 1 over x squared. And then we took the limit of each individual part. So what's the limit of 3? The limit of a constant is the constant. The limit of 1 over x squared as it approaches infinity, 1 over x squared. Where does it go? To 0. So it would be 3 minus 0 over 2 plus 0, which is 3 over 2. So we split it up so that we could get these to be 0. So what did we do? We divided the numerator and denominator by x squared. And why did we do x squared? The highest power on the bottom. All right. So again, all of that is a review that we did a few chapters ago. Okay. So occasionally you can extend these algebraic techniques to find limits of transcendental functions. For instance, the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. When I do direct substitution on the top, we would have e to the 2 times 0 minus 1. And then we would do it on the bottom as well. 2 times 0 is anything to the 0 power is, minus 1 is. On the bottom, anything to the 0 power is, minus 1 is. So it comes up to the indeterminate form of 0 over 0. It says factoring and then dividing produces. So I'm going to start back with the same thing that I just wrote. The limit as x approaches 0 of e to the 2x minus 1. The e to the x minus 1. When we look at that top, some of you don't realize that you can factor it, but you can treat it just like, and I'm going to write it over here, just like x squared minus 1. How would you do that? So if you have e to the 2x minus 1, what would that be? It's basically the same. E to the x plus 1 and did everybody see that? So on the top, I'm going to change this. E to the x plus 1, e to the x minus 1. On the bottom, I have e to the x minus 1. What happened? And then when I do direct substitution, what's e to the 0? What's 1 plus 1? 2. So we want to do everything that we can to get out of that indeterminate form. Not all indeterminate forms, however, can be evaluated by algebraic manipulation. This is often true when both algebraic and transcendental functions are involved. For instance, the limit as x approaches 0 of e to the 2x minus 1 over x. We already direct substituted this on the top and got 0. And on the bottom, if I plug in 0, I get 0. So rewriting the expression to obtain. Remember, anytime you have a monomial or one term on the bottom, this is like having like fraction addition or fraction subtraction. We can separate it out and put both parts over that monomial denominator. But this is going to give us another indeterminate form, and we haven't seen this one yet, which would be infinity minus infinity. How would you know for sure, like on this one, that it was going to be some kind of indeterminate form? That denominator is going to be 0. Everybody understand that? But when we put that e to the 2x over x together, it actually goes to infinity, and then 1 over x goes to infinity. So of course, you could use technology to estimate the limit as shown in the table, and from the table and graph, the limit appears to be 2. So we put this into y equals. We ask our table of values. You guys are okay with that? Remember how to do that. I'm going to go ahead and tell you what you get. On the first one, you get 0.865. And then you get 1.813. And then you get 1.980. 1.999. And again, we're looking for what happens as we approach 0. So that's the number that we're looking for. Here we get 2.002. 2.020, 2.214, and then we jump to 6.389. So again, as we get to 0, we have 1.999 and 2.002, which is 2. And I already told you that. But again, we did tables. You can do anything you want to. When you get to your AP exam, if they ask you to find the limit and you have your calculator, you can do it in a table. Doesn't matter. All right, so the new stuff. The Hospitals rule. It is fun to hear like my little Oriental college professor say this. Just so you know. Best day. And to find the limit of the function of the table, this is actually a really easy rule, and you guys will be okay with it. But again, that cheat sheet that you have, we're going to start doing derivatives again, so make sure you understand how to find the derivative. So we've been doing integration, and now we're jumping back to derivatives on this. That's why I kind of split it up. So you had all the mentality of integration, and then now we're going to kind of change and go back to those derivatives. So this is a really good review for chapter, whatever, like 4 to, so I don't know where we were when we did derivatives. All right, so to find the limit of the function in the table, you can use a theorem called L'Hopital's rule. This theorem states that under certain conditions, the limit of the quotient f of x over g of x is determined by the limit of the quotient of the derivatives. So f prime of x over g prime of x. To prove this theorem, you can use a more general result called the extended mean value theorem. So that extended mean value theorem, if f and g are differential on an open interval a to b and continuous, on the closed interval a to b such that g prime of x does not equal 0. Why do we not want g prime of x equal to 0? It's on the bottom. We can't divide by 0. For any x in the open interval a to b, then there exists a point c in a and b such that f prime of c over g prime of c is going to be f of b minus f of a over g of b minus g of a. To see why it's called the extended mean value theorem, consider the special case in which g of x equals x. For this case, you obtain the standard mean value theorem as presented in section 4.2. All right, so L'Hopital's rule. Let f and g be functions that are differentiable on an open interval a to b containing c, except possibly at c itself. Assume that g prime of x does not equal 0 because we don't want it to be 0 on the bottom for all x in a and b, except possibly again at c itself. If the limit of f of g over, f of x over g of x as x approaches c produces the indeterminate form 0 over 0. So this is the limit of your function as x approaches c. So it doesn't matter what that c is, 2, 1, 4, 8, infinity. So again, that's the easy stuff. The limit as x approaches c of f of x over g of x. But again, we don't want g of x to equal 0 because then it would be a 0 on the denominator. You can rewrite it. So those ones that we can't rewrite that still produce indeterminate forms, like on the front page, then we can do this. Find the derivative of the top over the derivative of the bottom, and then you can direct substitute. Provided the limit on the right exists or is infinite. This result also applies when the limit of f of x over g of x as x approaches c produces any one of the indeterminate forms. So these are all the indeterminate forms. Infinity over infinity, negative infinity over positive infinity, positive over negative infinity, and negative over negative. So we're going to start with 0 over 0. And like I said, the first couple are really easy. And as you get further along, that one's easy, that one's easy. So the next 2 pages or the next examples on the next page are pretty simple. As we get closer to the back, it gets a little more complicated. Like I had to stop, do the notes, come back to it. And I'm telling you. So when we get to those, I want a lot of time on those. If you have questions on anything that I did, like I literally had to write myself notes because I feel like I know exactly where you're going to ask questions because I had the same problem. All right, so make sure that you ask those questions because they're really hard to follow. All right, these are easy. We're going to evaluate the limit as x approaches 0. What does it do? When we direct substitute, we get 0 over 0. This is a direct substitution. So we're going to apply L'Hopital's rule. All that tells us is we're going to take the limit, and I'm just rewriting the problem right now. And then take the derivative. Of both the top and the bottom. Yep, sorry. That's what happens when you talk. All right, so go back to yesterday's test. When you integrate, how do you integrate? Add 1 and put it on the bottom right. What about when you derive? power in the front and subtract it. So it's completely opposite. Put it on the top and then subtract it. Is everybody good? All right, so e to the 2x. What is it? 2e to the what? Not x, but 2x. Why is this one not the one less power? Remember, what do we know about e? It's the same, right? So that one's a little different to start with. What's the derivative of a number? 0. So I'm going to go ahead and write that down just so you can remember that the derivative of a constant is 0. On the bottom, we have x to the 1. So what we have? You're integrating. Right. See, that's why I said, switch your brain back. Switch your brain back. So what's our power right now? That comes to the front. And then it's to the 1 less power, which would be what? 0. Right. So we do the limit as x approaches 0 of 2e to the 2x over 1. We don't even have to have that 1. I'm just doing all these steps so that when you go back, you can see where everything came from. Okay, so when you look at your book, it goes straight from like this to the very end. So you're not going to be able to look back in your book and see where it came from. Same thing like when we get further on, like I had to really work, like I had a separate sheet of paper like you guys were doing, and then like, oh my God, I missed a negative. Like it's rough. So just understand that I know where you're at. You just got to ask questions. So the limit as x approaches 0, of 2e to the 2x. Now we want to try to direct substitute and see if we get an indeterminate form or if we get an actual value. We're not going to get an indeterminate form because we don't have a denominator, right? Does everybody understand that? So plug it in. 2e to the 2 times 0. What's 2 times 0? Anything to the 0 power is. So our limit is 2. So if we go back to that first page, guys, and I'll uncover this in a minute. This is what we did right here. They gave it to us here. We split it up. And we could see it's still indeterminate. So we did the chart, which took forever if we actually did it. So then now what they're saying is you can apply this rule and it makes it a little bit quicker. Okay. What takes the longest is the simplification. I do not need to see all of this work. That is just for you when you go back to look at it. Okay. In the solution to the last example, note that you actually do not know that the first limit is equal to the second limit until you have shown that the second limit exists. In other words, if the second limit has not existed, then it would have not been permissible to apply L'Hopital's rule. So another form of the rule states that the limit of f of x over g of x as x approaches infinity or negative infinity produces the indeterminate form 0 over 0 or infinity over infinity then the limit as x approaches infinity of f of x over g of x. It's the same thing. Take the derivative, provided that the limit on the right exists. All right. So if we split this up and we're looking at infinity, what's going to keep happening to this graph? What's going to keep happening to this graph? It's going to keep going to the right and up, right? So what is the limit as we approach infinity? Infinity, right? So that ln x is going to produce infinity. If I put in my 1 over x, sorry, and I graph it, what's going to happen as we keep going? Okay, so see how on the right, it's like it's just that one curve and they're opposite. So like, what about if this one went to 0? Let's talk about that for a minute. What if we looked for the limit, just this function as it approaches 0? Why? Yeah, so we got to go back to limit thinking. It doesn't necessarily that it doesn't touch 0. It's that what happens at 0. What happens at 0? What's happening to this graph? You can see this graph. What's happening to this graph at 0? Okay, what's an asymptote do? Yeah, but let's talk about this. What is the limit from the left? Limit as x approaches 0 from the left. Negative infinity. What about from the right? So why does the limit not exist if I just put 0? No. It didn't touch 0 on the left or on the right, but you said it was 0. I mean, you said it was infinity. What happens if I just label 0?
Because it's not going to infinity. It's just sitting there. So, I mean, if it's going to 0 and it's not infinity.
Okay, let's do this one more time.
Oh, see, that's the best we got.
No, it's not. So I'm not, we got to get back in that mindset. So I'm trying to get you back in that mindset. So understand that I'm not upset that you don't know this. We've just got to, we got to get back in that mindset. So infinity from where as x limit, as x approaches 0 from the left, what is it? From the left, negative infinity. Why is it negative infinity? 3 points down, okay. From the right, as we approach 0, positive infinity, but what if I don't put the little plus or the minus and I just say 0? Why does it not exist? Because you just told me it existed on the left and on the right, but why doesn't it exist if I don't label it left and right? Say it a little bit louder. Oh, they're supposed to hear you, but they're going opposite directions. They're going in opposite directions. So because they go in opposite directions, the limit doesn't exist. So remember, we talked about on the right and the left, you're going to start seeing the right and the left come back in. Why do they do that? Because we can't do the infinity as x approaches 0 because it's indeterminate. It's that crazy, goes in opposite directions. So when we look at this, that's what we're talking about. So go here and tell me what I can do to this. Can I divide it by the x? Is it going to do anything? No, because I can't do the limit of x over x. Still going to give me the same thing. So what I'm going to do is take the derivative. What is the derivative of ln x? 1 over x. Good job. So we got the limit as x approaches infinity of 1 over x. On the bottom, the derivative of x is 1. So this is actually the limit as x approaches infinity of just 1 over x. As we go to infinity, that's this way. Where does this graph go? Where does it go? 0. Remember, that's why we try to get it to look like this, because anything 1 over x is going to give us that 0. What? I mean, you don't bother me. When's the last time we did limits? It's been a while. It's been a while. Hopefully it's a little bit coming back.
It's so hard to go from integration to derivative.
Which is why I didn't put it on the same test. Does that make sense? So we've got time. Yeah. All right. Occasionally it's necessary to apply the rule more than once to remove an indeterminate form as shown in the next example. So you need to test it every time. Like we're literally testing this. You just don't realize it because we're not getting another indeterminate form. So this is still a test when you're direct substituting or you're graphing it or whatever. Also, if you want to, I graphed this so that you could see that it goes to 0, but you should know that 1 over x gives you 0. And we did that in the very beginning. So when we did this one, when we had the 1 over x squared and the 1 over x squared, you said it went to 0, right? So that was why we did it, so we could eliminate that. Okay, so nothing new. You already knew that. So now let's look at this one. All we're doing is taking the derivative and we're going to test it out again. So x squared, remember, is the U shape. So x squared looks like this. So as we go to negative infinity, where does this graph go? Negative infinity is on the left. As we go to the left. Mhm. Here is your e to the negative x. As we go to negative infinity, what does it do? Positive infinity. That makes an indeterminate form. So we're going to take the derivative of both. What's the derivative of 2x? I mean, x squared. No. There you go. 2x. What's the derivative of e to the negative x? E to the negative x. So it's the same. All right. So we're going to graph. As we go to negative infinity, what does this top part do? Negative infinity. Negative e to the negative x. When we graph it, where does it go? Look at it. We're going to negative infinity, so we're going to the left. Negative infinity. So there's your other indeterminate form. So it says you can derive it again. Derive it again. So the limit as x approaches negative infinity. What's your derivative of 2x? Derivative of negative e to the negative x. E to the, say it again, sorry, negative x. As we go to the left, where does it go? Zero. Bless you. In addition to the forms 0 over 0, and infinity over infinity, there are other indeterminate forms, and we've already went over those. But there's these as well. 0 times infinity. 1 to infinity. Infinity to the 0. 0 to the 0. And we already saw infinity minus infinity. So for example, consider the following 4 limits that lead to the indeterminate form 0 times infinity. So just to give you examples. So the limit as x approaches 0 of 1 over x times x. Did you get what you needed? You wanted what? They have them. You want me to look one up for you? Do you need it like right now?
No.
Okay, I'll look it up in a minute.
so I can have it for money to back up the phone. Flying solo.
Sorry, y'all. I think there are some. All right. The limit as x approaches 0, what happens right here? Again. We just talked about this. Look at it. We didn't talk, we did talk about it. What's gonna happen? As it approaches 0, let's say from the right or from the left. 0. If I do, no, it's not 0. It's not 0. From the right or the left, approaching 0. Negative or positive, depending on the side we come from, right? Does everybody understand that? Or it does not exist. If we go into this one, sorry, y'all. His ass sheets threw me off. What's this one? As it approaches 0, 0, the coordinate is 0, 0, right? So that's the one where your 0 comes from. So this one's going to be your infinity, and that one's going to be your 0. The actual limit of this is 1. How would you do that? Do your derivatives. All right, another one. These are just examples, again, of the 0 times infinity. The limit as x approaches 0 of 2 over x times x. If you direct substitute, you're going to get that. Think about this too. If I have 1 on top and 1 on bottom, what's going to happen? Cancel out. So what is this one actually going to be? That makes sense. But if I direct substitute, it's going to give me the wrong answer. Okay. Limit as x approaches infinity. Of 1 over e to the x times x. This actual limit is 0. You would get an indeterminate form, then do the rule or check by your graphing. And then one more, the limit as x approaches infinity of 1 over x times e to the x. And that actual limit is infinity. And again, we can go find those, but we're not going to right this moment. Let's finish this paragraph and then we'll be done. We won't do the example till Monday. Because each limit is different, it is clear that the form 0 times infinity is indeterminate in the sense that it does not determine the value or even the existence of the limit. The remaining examples in this section show methods for evaluating these forms. Basically, you attempt to convert each of these forms to 0 over 0 or infinity over infinity so that L'Hopital's rule can be applied. And then we'll stop there and work the rest.